Hello guys, welcome back again to this tutorial on final exam preparation with me for Intro to AI and Data Science class. In this session, we will talk about several topics that may come up in your exam, such as neural networks, regression, as well as generative AI. We'll talk about that briefly at the end of the session. The first one is neural network. So to recall again, this is the typical architecture of neural networks. It consists of input layer, several hidden layers, and the last one is output layer. So in this picture, you can see this is basically a densely connected neural network, which means each neuron in the K layer is connected to all neurons in the K plus 1 layer. So as you can see here, let me turn on my laser. Okay, so if you can see this neuron over here, it is connected to the first neuron in the input layer, the second one as well, and the third one, and the last one is the fourth one. So it is connected, densely connected actually. And perhaps the lecturer had shown you in class about um, this utilization of Keras library in constructing neural networks. And perhaps if you remember, the lecturer used this kind of layers called dense layers. So basically, this is the dense layer that the lecturer used in that session. So the densely connected layers, as I've explained before, it is connected. It's fully connected. Okay, so let's continue. The next one we are going to talk about this architecture of single neuron. It means this one. What happened? What computation occurs in this one neurons? So basically, there are several components of this single neuron. There's input, the weighted sum over here, the activation function, and the last one is the output. So each connection to this neuron has its own weight. Basically, this W1, W2, and Wn is the weight that I'm talking about. And this weight can be adjusted during the training process. But if you are into machine learning and kind of transfer learning kind of stuff, not all of layers, I'm sorry, not all of weights can be trained. Sometimes you want to freeze them and just kind of like adjust um, the weights on the some layers before the output layers. Yeah, that's just some kind of like engineering tricks to make your models become better than before. Um, the weighted sum combines all the input values from previous layer with their distinctive weights, and this activation function actually allows this neural network to discover nonlinear patterns in the data. So there are several kinds of activation function. It could be like ReLU and sigmoid and tan inverse, and yeah, there are so many of them. And the weighted sum result would be, for in this case, the x1 times w1, so the input value and times by this weight, and the x2 times w2, and so on until it reaches this xn times by wn. And if you take a look closely, this is actually the dot products between um, a row matrix and a column matrix. So if you are training a large number of neural networks, then you will work on a lot of like matrices. And after getting these z values over here, which is actually the result of this weighted sum, we have to plug in into this activation function, which the result would be a, and f is actually the activation function I've talked to you before. And there are several kinds of them. Um, the identity, binary step, logistic, 10H, um, Arcus tank, and yeah, the time inverse and ReLU, preLU, and so on. And basically, um, if you are using identity, um, actually you are not using activation function, because it just the input and the output is the same, so there's no use of that. um, there are so many of them, so which one to use? Actually, it depends on the context. And for the exam, I guess it will be specified explicitly in this instruction. Let's continue. So the training process in neural network. So basically, there are two main parts in during the training process of neural networks. The first one is the forward propagation, which you calculate all um, the value of the neurons until you get this output, and you get this predictions value. After that, um, you have these true values, and you can compute the error of using this loss function over here. You get this loss score, and then you want to go back again and just kind of like adjust all those um, weights in this previous layer, and then you go back again and you want to adjust the weights in this layer again until it gets to the first layer. After that, you will do again this forward propagation. You get this prediction and compare it again to the true values, compute the loss function, and then you will do this back propagation again. So back propagation, as I have explained before, is the process to adjust the model's weight. And it's very complex, involves a lot of like calculus stuff, especially in partial derivatives, because we are doing basically gradient descent, chain rule, and yeah, some kind of like calculus stuff. And if you are interested in learning this kind of like back propagation, you can check out this YouTube video, as I want to explain um, the concept of this back propagation here. As long as you understand how back propagation, how forward propagation is computed, it is very important. So let me just continue to this example of computation of this forward propagation. So um, take a look at this neural network over here, and using this arctan activation function, you want to compute the value of A12. So what does it mean by saying A12? This 2 over here is actually um, the layer, and 1 is actually the neuron over here. So this is the first neuron, the second neuron, and this is the bias. To compute A1, you have to compute this one first, the Z12. So it is basically Z12 after being plugged into activation function. So this C is basically the result from the weighted sum. So to compute the Z12, we want to do some calculations here, the dot product, such as like 0.4 times by 0.3 um, plus this 0.8 times by 0.5, and the last one is 1 times by 0.1, which is actually the bias. So this is the result, and you get this 0.62, and then you can just simply plug the result of this Z12 into activation function, which is actually the arctan activation function, and you get the result of 0.55. You can actually use the same method to compute the value of the output layer, or this A1 of layer 3. Yeah, just a simple computation, I guess. A12 times W112 A2 of layer 2. I'm sorry, where is it? Oh, this one. A2 of layer 2 times W12 for layer 2, and added by this bias over here. So in this case, all of the weights are trainable. You want to adjust this during training process so you can get the desired output, or you can minimize the loss function. After computing this weighted sum, we can just simply plug this into the arctan, which is actually the activation function, and then you can get the result of this output layer. And you can evaluate it and compare it to the ground truth or the actual value using loss function, and then you can do back propagation. So since this is an iterative process, you want to do that a couple of times until you get the desired result. Okay, let's continue. The next topic we will talk about is regression. Um, what is the difference between classification and regression? So basically, classification, as you have learned before, it is kind of like we are tasked to predict discrete values or categorical values, whereas this regression, we want to predict a numerical or a continuous values, like this one. Um, I took this example from the slides. Okay, so there are three types of regression which has been taught in the class. The first one is the simple linear regression. So basically, in this simple linear regression, it is the same with linear equation that you have learned back then in the high school. This y equal to m times x plus c, where m is the weight of the variable and c is the bias. And do note that the bias we are talking about here is different to the one that you have learned in bias and variance topic. And in this simple linear regression, um, we are tasked to find the most suitable m and c, and that minimize the error function, or the error of the loss or the loss function. We want to minimize this loss function, so we can do optimization task. So if you still remember about numerical analysis topic on gradient descent and optimization, it is used actually in this linear regression. You can use steepest descent, gradient descent, or even like exact Newton method, which incorporates the computing of the second derivative. You can use that to determine the value of m and c. So this is the simple linear regression. Um, Basically, in this example, we are trying to predict the happiness score based on the income. So the x-axis is the income over here, and the y-axis is the happiness score. And in this example, we got y equal to 0.2 plus 0.71 times by x. Um, but here comes the problem. Um, in the real data, you are not working with only one feature. In fact, you are working with a lot of like features, like several features. So if you want to predict the dependent variable based on several independent variables or the features, then we are going to use multiple linear regression, which is actually the generalization of this simple linear regression. So we are actually incorporating more than one features in this equation. The notion is, pretty straightforward. Just like the simple linear regression, trying to find the best wi in the equation below, where all of xi are the features we are going to utilize to predict y. And we can use the same loss function as well. The plot will be in a dimensional space with n minus 1 is the number of features. Like for example, if you are working with two-dimensional space, you only take one variable into account. But for example, if you are working with two variables, in this case the temperature and the income, then you will get the result in a three-dimensional plot. But unfortunately, not all of data can be fitted into linear models. So this is the simple linear model we have talked before, which only consists of this straight line. It forms the straight line because by nature there are some data that possess quadratic quadratic distribution, cubic distribution, and etc. Um, so you need actually a higher order polynomial regression. And why do I say this as a higher order? Because this linear model is actually a polynomial itself, but the order is 1. So this is the polynomial model, and when the order is 2, or the highest order is 2. It's basically the same. You can see this degree 0, you can get the straight line. Degree 1 is straight line as well. Degree 2, it forms a graph like this, and this is the degree 3 polynomial. The training process is basically the same, trying to find this trying to find this coefficient of x squared, coefficient of this x, and the bias. So there's a problem when you are working with polynomial regression. You have to be careful when determining the order of polynomial you want to use in your project, because the higher the order of the polynomial, as you can see in this graph, the more it could fit the data well. You can see the pattern over here. For the ninth order polynomial, it can capture the data pattern very well. But sometimes it could lead to another problem, which is actually overfitting. So it fits the training data very well, but unfortunately, the model can be generalized to predict the unseen data. So that's a big problem. So you want to avoid this overfitting and the underfitting in your polynomial regression. So this is kind of like trivia. If you still remember about linear algebra, the problem we talked before is actually an over-determined systems of equations, which is actually the number of variables we are trying to predict is more than the number of data points or equations. So we can actually solve this using normal equations, this normal equation over here, but it is not used commonly because of these reasons. So this is basically computationally expensive when you are asked to compute the inverse of a matrix. So because we are trying to find the x, we have to compute this inverse of this A transpose times A matrix. And the second one is because this numerically unstable issue when inverting a matrix, especially when this matrix is close to singular. So it is very hard to, it's not very hard, but it is unstable. The condition number is very high. And so as I have told you before about this gradient-based optimization. Nowadays, people use this gradient-based to determine the weight, to optimize the loss function. And for the evaluation matrix, we have this 4 as the evaluation matrix. The first one is this mean absolute error, mean squared error, root of mean squared error, and the last one is r squared. And since MSE is proportional to RMSE, since RMSE actually the root squared of this MSE. So if you are working with MSE, you only take this one inside this root square. Sorry. Whereas for this AE, you are working with this absolute error. And you want to sum it and divide it by the number of data points, or to put it simply, you are working with the average of this absolute error. So this is the example of the regression evaluation matrix, and perhaps I would like explain to you about these slides first. yeah, in RMSE and MSE, um, the errors are squared before they are being averaged, as you can see over here. It is squared before being averaged. So um, they both give a relatively high weight to large errors. So if you want to avoid large errors specifically in some instances of your data, and using these metrics would be useful. And RMSE actually is in the same unit as the dependent variables, making it very easy to interpret and understand the errors compared to MSE. Like for example, if we take a look at this one, evenly distributed errors would produce the same result of MAE and RMSE. When there's small variance in errors, um, it's quite different compared to MAE and RMSE. But for this large error outlier, it would give this RMSE a very high error. Meanwhile, for this MAE, still produce the same result. So if you want to avoid this kind of like error in your models, then you should use this RMSE. The way you can utilize this is by um, if the RMSE is very high, that means that you have to adjust the models again. Okay, let's continue. The example of error analysis. So perhaps, like for example, you have this data over here. This is the real one, and this is the predicted one. If you want to compute this MAE, MSE, and RMSE, it is pretty simple. You can compute the absolute value of the difference between these two, which is actually 1, and you can compute for the other instances of data, and the same as well for this one. The difference is that it uses this kind of like squared error. So you want to compute the difference, and then you kind of like exponentiate it by 2. After that, you can sum all of this, and for this MAE, you can just like 13 divided by 10. You can get this 1.3, and for this MSE, you can get this 2.1, but this is not in the unit of the input. So we want to take the square of this one to get this RMSE, and you can get this 1.45. So this is the example of error analysis. The last topic we will talk about is generative AI. The scope of AI. This is the scope of AI that perhaps I guess like this material has been explained in the class before, but I just want to recall it. So the generative AI is a subset of deep learning, which is actually the subset of machine learning, and machine learning is the subset of artificial intelligence. So if you are asking, is ML a proper subset of AI? The answer is yes, because machine learning only works with data. You can see this. Subset of AI that enables machine to learn from existing data and improve upon that data to make decisions. But there is another subset of artificial intelligence, which is actually using some kind of like knowledge based, and this is why it is called the knowledge driven AI. And for the subset of machine learning, um, there are another conventional machine learning that doesn't involve this deep learning, such as the random forest or um, KNN, knife base, and so on. And the same as well for this generative AI, it is not a proper subset of deep learning, as we can use deep learning for another um, complex task, not only generative AI, such as we can do um, as simple as perhaps sentiment analysis using deep learning after converting all of your text into embeddings and so on. There are so many examples of the usage of this deep learning. not only generative AI. And the next topic we will talk about, which actually um, the last topic, is on how to generate good responses from AI. So actually, based on my experience, there is no absolute way to formulate prompt so that the response fulfills 100% of your information need. I mean, like, it's just like using the search engine. You must go through trial and error processes to get the desired response from AI. And there are several tips that might help. Um, I get this from the slide. You can read that from your slide as well. But I guess the most important one is the first one. You have to be specific as possible. And you can practice using ChatGPT or Bard to enhance your prompt engineering skills, as this kind of skill is very important nowadays. Okay, I guess um, that's all for the presentation today. Um, I hope you can succeed in your exam. And if you have any further questions, you can just ask me online or another media that you prefer. Thanks and good luck.